Have you ever really stopped to think about how a tiny little rubber duck and a gigantic, massive steel aircraft carrier can both float? I mean, it's one of those things we just kind of accept, right? Well, today we're going to unlock that secret. And it's all thanks to a fundamental principle of physics that was discovered, and you're not going to believe this, in a bathtub over 2,000 years ago.
I mean, think about it. You toss a tiny little pebble into a pond and whoosh, straight to the bottom, no question about it. But then you have this enormous ship made of thousands and thousands of tons of steel just cruising along on the surface. How does that even work? It feels like it totally defies common sense. But, there's a powerful hidden force at play here. So what is it? Well, the answer comes down to this invisible force, a constant upward push that the water itself is always exerting on anything you put in it. This force, this push, is really the secret hero of our whole story. So let's dive in and figure out exactly how it works. Okay, so to really understand this hidden force, we have to do a little time traveling. We're going all the way back over 2,000 years to ancient Greece, and we're going to meet the brilliant mind who first cracked this code, a guy named Archimedes. Eureka! You've probably heard that word before, right? It's pretty much the most famous aha moment in the entire history of science. It's that shout of pure joy when you suddenly figure something out. And let me tell you, the story behind this particular Eureka is just as awesome as the discovery itself. So the legend goes like this. King Hiero II gets this beautiful new crown, but he has a sneaking suspicion that the goldsmith cheated him, that it isn't pure gold. So he calls in Archimedes and gives him a puzzle. Prove it, but you absolutely cannot damage the crown. I mean, what do? Archimedes is stumped, just racking his brain. Then, one day, he's getting into his bathtub and he notices the water level rising as he gets in. And that's it. That's the light bulb moment. He realized the amount of water he pushed out of the way, the displaced water, was the key to the whole puzzle. And that moment right there in the tub led him to this incredible principle. Let's just break it down nice and simple. When you put anything into a fluid, like water, it has to move some of that fluid out of the way, right? It displaces it. Here's the magic part. The weight of that water you pushed aside is exactly equal to the upward force that the object is now feeling. That's the buoyant force. Okay, so we know what the principle is. That's a huge step. But now let's get into the nitty-gritty. Let's talk about the mechanics. What is actually creating this incredibly powerful upward push? Okay, just imagine the water pushing back. As you lower an object into the water, it has to shove that water aside. And the more water it moves, the more the water pushes back. Think of it like this. The water is pushing on the object from every single direction. But, and this is the key, the pressure in water increases the deeper you go. So the water at the bottom of the object is pushing up harder than the water at the top is pushing down. And that difference creates a net upward push. It's that simple. So here's the secret formula, the heart of the whole thing. The buoyant force, that upward push, is simply equal to the weight of the fluid that got pushed out of the way. That's it. It's like a cosmic balancing scale. On one side, you have the object's weight pulling it down. On the other, you have the weight of the displaced water pushing it up. All right, so this brings us to the main event. The big question, will it float? It all comes down to a battle of forces, a simple tug of war between up and down. So let's look at the two competitors. In one corner, pulling everything downward, you have the object's own weight, thanks to gravity. And in the other corner, pushing upward, you've got that buoyant force we've been talking about, all thanks to Archimedes' principle. Whichever force is stronger wins the fight. And really, there are only 3 ways this battle can end. Outcome number 1. If the object's weight is more than the buoyant force, gravity wins and the object sinks. Simple as that. Outcome 2. If the buoyant force is stronger than the object's weight, the object floats. And then there's the third really cool outcome. If the two forces are exactly equal, the object is neutrally buoyant. It just kind of hovers there in the water, not sinking, not rising. Think of a scuba diver or a submarine just chilling mid-water. You can actually prove this to yourself with a simple thought experiment. Picture a bucket of water filled right to the very brim. Now, you gently place an object into it. Naturally, some water is going to spill out over the side, right? Well, that spilled water is the displaced fluid. If you could collect all that spilled water and weigh it, and you found out it weighed more than the object you put in, you'd know for a fact that the object would float. It's that direct, that predictable. It's just physics.
So this is way more than just a fun science experiment. This principle is, and I'm not exaggerating, the absolute bedrock of so much of our modern world. It's at work all around us, every single day, sometimes in places you'd never expect.
And this finally brings us back to our big puzzle, the giant steel ship. Okay, so a solid chunk of steel, yeah, that's gonna sink like a rock, no doubt. It's super dense. But when you take that same amount of steel and shape it into a huge, hollow hull, what have you done? You've trapped a ton of air inside. Now the ship isn't just steel anymore. It's steel plus all that air. That makes its average density way, way less than the water's. And because it's so huge, it displaces an enormous amount of water, creating an upward buoyant force that's strong enough to hold up the entire thing. It's all about the shape.
And once you start looking for it, you see this principle literally everywhere. Submarines? They're masters of buoyancy. They pull water into special tanks to get heavier and dive. Then they pump that water back out to get lighter and surface. It's genius. And get this, hot air balloons work on the exact same principle, just in the air instead of water. The hot, light air inside the balloon displaces a huge amount of the colder, heavier air outside, and that's what lifts it up. Even simple little tools like hydrometers that measure the density of liquids are just floating based on this same amazing rule. Just to really put a pin in how powerful this force is, think about a modern aircraft carrier. We're talking about something that can weigh up to 100,000 tons. That's 200 million pounds of steel, airplanes, fuel, and people. And yet, there it is, floating. It's just incredible. And it's all resting on that simple, elegant principle that Archimedes figured out while taking a bath. The amount of upward force required is just mind-boggling. So, at the end of the day, Archimedes' principle isn't just about things floating in water. It applies to any fluid, and that includes the very air we're all breathing right now. It's a perfect reminder that there are these incredible, invisible forces constantly at work all around us, shaping our world in ways we barely notice. And that kind of makes you wonder, doesn't it? What other invisible forces are out there, quietly lifting, pushing, and holding our entire world together?